introductions, and now I will try to share my screen. Let me know if my screen is visible in the PowerPoint full screen mode.
Yeah, it is visible in the PowerPoint full screen mode.
Thank you. Okay, so thanks everyone. Thanks to Pratesha, Darshan for giving this opportunity to talk a little bit about my area of work, what I am currently engaged. And just to add on already, I think you get to know a little bit about me. So on personal front, I am out of, basically I'm from Kolkata, Bengali, currently working in Pune for Philips Healthcare. And I have total 17 years of experience working in the domain of healthcare as well as power system related products. So of course, in my leisure time, I would like to read some historical topics, and I do love to visit some places related to that, and that give me a lot of good feeling. I learn some Indian in music, play, and very often I get time to do so. So with that said, I will move to our topic of discussions today. So, so I will be first talking a little bit about what is X-ray, followed by why this high voltage design is important for X-ray related products, something on theory, how this is managed during the design and development phase, insert level, as well as in the casing or the enclosure level, and followed by the second part of the presentations on high voltage power supply design, which is required to produce or power up the X-rays. So when you talk about high voltage design, so as such, that high voltage word does not come up with a tag of how much voltage is really high voltage. So the definitions what I got from wiki is what I'm showing it. So it varies. Few cases, if you are in a electronics industry, 50 volt itself is a high voltage. And if you are in power sector, definitions is different. And in the below table, that's what I learned when I work in Rekem RPG, that these are their definitions of low voltage. So 11 kV they considered as a low voltage, and 132 kV and above is called as high voltage. So now for the X-ray industries, we have similar in a product level, we have different kind of voltage required to functioning of the product. So anything which is required above 40 kV, that we classified as high voltage. So that means that comes under my design area. Anything below that, which are maybe the job of the power engineer, what I call here, who works on mostly up to 750 volt DC. Okay, so it's just some fact, like why people are so much serious when we talk about high voltage. The first thing comes shock. However, we all know in this forum that it's not the voltage, it's the current which is responsible for giving us the shock. And uh, due to human body resistance, the amount of current which is really shocking is not depend on a particular voltage level, rather it depends on body resistance level, which continuously changes time to time. So hence there is no point to think that up to this voltage it's not fatal. Even something as low as 230 volt can be a fatal. I'm not going through any YouTube links because this team is well matured and I don't want to show some other informations. Now coming to the topic, X-ray. So before we go to the design of the X-ray device, let's have a look at what is X-ray. So just a minute. Yeah, now it is better. Yeah. So X-rays is a form of powerful electromagnetic wave. So we are the visible light. That's is, I don't know if there is a pointer. Yeah. So the visible light that's operate in this frequency and wavelength range, whereas X-ray comes 30 pentahertz to 30 exahertz in that range. This is the range of X-ray. So it's the same power radiations, electromagnetic radiations, or electromagnetic wave of this particular frequency and voltage. And it has a power of in the band of 10 electron, 100 electron volt to 100 kilo electron volt. So how this X-ray is produced? X-ray is produced when a highly accelerated or highly kinetic energy electron collide with a solid body. The electron himself get absorbed on that metal part, and the kinetic energy with which it collide with that metal part get converted into a electromagnetic wave which emits from that solid surface, solid metal surface over which it was collided. So that's how X-ray is produced. If we go little bit depth of that, so as I explained just in the previous slide, that a highly energetic accelerated electron needs to collide with a solid metal surface. That's how it is done. There is a what we call filament, which is exactly same like what we see in the old days uh, incandescent bulb. Electrons, free electrons are generated with the help of thermionic emission. And then once these free electrons are available, there is a high potential difference between cathode, C stands for cathode and A stands for anode. A very high potential difference applied between these two. And because of that potential difference, electron will be getting attracted to the positive electrode anode, and it get accelerated during this travel, and it hits this solid metal. It get absorbed here. It result a current in this flow because the electron get absorbed here, and the kinetic energy with which it collided that get converted to a powerful electromagnetic radiations, which is X-ray. That's how it produced. So if we see that how do you create a in a highly accelerated or high velocity electron, that is basically done by the electric field. So we know that electron energy is charge multiplied by electric field. So charge of electron, you cannot change any, cannot do anything. Electric field is proportional to the voltage applied between these two. If I consider the space between these two is constant. And hence, uh, this energy is built up. More the voltage difference, more the electric field, more the kinetic energy of the electron, and powerful will be the radiations which comes out due to stopping of this electron. We see that 40 kilovolt to 150 kilovolt, that's the operating voltage of any X-ray device, which is used for diagnostics, human diagnostics purpose. Anything below 40 kV, it will not result X-ray, which means it cannot penetrate the human body. Anything above 150 kilovolt will result such a powerful radiations which will just kill the electron, which will kill the human cells. So which is not X-ray, that's basically comes under gamma ray, which is also used for cancer treatment and some other treatment purpose, not for any diagnostics or imaging purpose. Moving to the next. So now we try to explain how this X-ray generation is happening. So next is our topic, high voltage design. So what is high voltage instability or the breakdown? So as I say that there is a huge potential difference between cathode and anode, and the media between these two should act as a insulator, not as a conductor. Moment it becomes conductor, there will be a erratic flow of electron, which we know as arc. As if in X-ray industries we call the arc as spit also. Spit is the short form of spurious instability and transiency. Okay, so what I say that instability means the insulation criteria between these two electrode converted to a conduction criteria, hence we call it instability. Compared to normal high voltage engineering, there is a slight difference. I say the electron has to flow. Normally in high voltage engineering, through insulator, no electron flow is allowed. But for X-ray, that's a bit different story. You need to have controlled electron flow between cathode to anode, uncontrolled or unwanted electron not to be flow between these two. If flow, then it's unstable high voltage design. Well, now coming to the point that why this breakdown and how this breakdown is happening. That's, I think now this is something what all high voltage engineer are aware. It's like the Townsend breakdown criteria. If you have some electron, it just go on multiplying and it creates a avalanche, and then it just converted a plasma or spark between these two electrodes. Same thing applied. So theory remain the same. That's how the puncture or the I will not say puncture, it's a instability between cathode and anode happens. So there is nothing to puncture. It's not puncture. So what we do here, you can see a commercial rotating X-ray tube, which is used nowadays for different applications, being a radiographic or CT or any other applications. So this is what we were talking about, cathode, anode, and inside this cathode, there is a filament which is responsible for generating the thermionic electron, and then they travel from this to this and produce X-ray. And between these two, we have to have a high voltage stability. So we need to reduce the air pressure, air molecule, to avoid any Townsend's that avalanche breakdown. So any X-ray device, basically a vacuum tube, and the vacuum level on which the medical X-ray device operate is 10 to the power minus 6 torr. That's the ideal level. It does not result any arcing between cathode and anode. Up to 10 power minus 4 torr, it works. Below that, it becomes high pressure and it results a arcing between cathode to anode. And this change we will see soon, because when you go on using the tube for long time, especially for surgery or CT applications, the temperature increases, and again vacuum level come down from -6 to -4. But if it comes below this, then it will not work. And you can see where we stand in medical X-ray tube. It's in this region, whereas the earth orbit and interstitial space, it's on this region. So like I say, for a long duration applications where X-ray is produced for a considerable long time, the temperature inside this vacuum tube, all this metal component elevated. How much? It can go as high as 600, 700, 800 degrees centigrade inside. And it tend to dissolve the gases again, because we heat it, it start emitting the gases and it loses the vacuum. So there is a second level of design. Even though we achieve the required vacuum, we put some active pump inside the device. Its concept is to some extent similar to silica gel of a transformer. You can say silica gel go and absorb the moistures, and this active pump, it's a chemical pump, so it emits some kind of powder of these materials, and it start absorbing those gases. Hence again it bring back the pressure inside the device to lower side. So there are some, we call it getter, not, we do not call it active pump. And there are two type of such thing. One is bulk getter, which need to be kept at elevated temperature throughout the functioning, which means it needs a small power supply which will heat up that devices. And there is a concept called flash getter, where one time with a high current, we create a high temperature, it just got evaporated and get deposited. And throughout the life of the X-ray tube, we do not have to do anything. Those deposited powder do their job, they absorb the gases. So that's how the vacuum part of the X-ray tube is taken care by vacuum level design and the getter design. Coming to the next point, it is very important to also maintain the required distance between these two, because I say that the X-ray tube has to operate 40 kilovolt to 150 kilovolt. Same tube will work 40 to 150. So it's important to design the distance between these two. So here comes a kind of design conflict, what we say. High voltage design is fine. So from high voltage design, we say we need more gap between these two. More gap means more insulations, less chances of failure. Whereas people who are doing the optical part of the design, they need a smaller distance between these two. Why? Because as I say that X-ray will be produced from this metal surface, and if you have a big distance between these two, the electrons will scatter, will have a fanning effect more. Hence, the area from which X-ray is getting produced, the length and width will be higher, and higher the emission area of any light source create a image artificial or image blurring effect, because we all know a big light is basically a summations or the accumulations of many small light source. So in X-ray also it's equally applicable. So if you have a bigger size of what we call in our terminology focal spot from which X-ray emits, if you have a bigger focal spot, you have more probability of image artificial effect. And hence they need very small, high voltage needs very big. And here comes a design compromise or optimizing both the requirements so that both the functional requirement meet. So how this high voltage, we use again some of this numerical tool to optimize, and based on the guideline established internally, we operate the distance between these two. Another
Hello,
critical
sir.
point. What? Yes, hello.
This is Balaji. Can you go to the previous slide? I have a question.
Yes.
Yeah. So, isn't the gap decided upon the amount of mean free path for acceleration so that you can get that much kinetic energy?
Yeah, typically this gap will be in the order of 11 millimeter to 16 millimeter,
Mhm.
which
That
is
is to
quite a, yeah.
that is to
And
accelerate and get the required kinetic
yeah,
energy.
yeah, yeah, yeah. 11 millimeter and 16 millimeter, typically it is okay, you are above that mean free path. However, the optical requirement and high voltage stability plays a major role here. And we don't want here the electron to create a secondary emissions, because we want only thermally emitted electron go and hit. If there is more branching, more secondary electron creation, it tends to a failure. That's what the vacuum and all these things come. So our experience says 11 millimeter to 16 millimeter with 10 power minus 6 torr pressure, it just optimal.
Okay. Also, do you use a rotating anode design or a
Yes.
static anode design?
Generally, all major X-ray tubes rotating anode.
Okay.
Only few applications like dental, which is a small power X-ray, it's static anode.
Okay. Thank you.
Yep. Going to the next slides. So one of the critical, another failure mode that's also very known to the high voltage engineer, that's the triple point. So as we say in vacuum, triple point means junction of glass, metal, and vacuum is a emitter point of electron. So we need to take care during this high voltage design, all the triple point are properly shielded and they are not exposed, hence reduce. So again, that software tool, ANSYS or other console are used to properly evaluate that after shielding the stress coming below the any alarming limit. Third point, the next point, what we ensure the surface finish of the cathode and anode. So what we see that due to rough surface, it's a very, there is a 10% reductions of the beta factor, there is a 80% reduction in the emission, field emission. So that's what that surface roughness plays a very clear, a very crucial role, and we do take care and give a specific surface roughness guideline so as to get the high voltage stability. Not only surface roughness, we generally try to evaluate in a, that's normally happen if a troubleshooting needs to be there, that beta factor, because beta factor is a little bit above the surface roughness. If you have a curve bend electrode inside vacuum, generally due to the curvature, you have a high field. On top of that, if you have a rough surface, that's more dangerous compared to having a rough surface over a flat surface, over a flat part of the electrode. So that's what we say, that if you have the beta value within this immaterial, whether it is a rough curve or flat, you will meet that. So that's what we, some cases we try to do checking of the beta, and it's not something we can do theoretically. We really need to perform the experiment and obtain that factor. So that's what we explained, that we want the electrons of thermically emitted to reach to the anode. Any electron which comes from the cathode flat part, they are field emitted. We do not want. That's how the smooth design, avoid the curve, etc. is done. So long, what is the critical steps we discuss? High voltage clearance design, vacuum level design, getter design, and the surface finish. Now we come to the next level. Of course, any,
Also, sir, one
yeah.
more question. So, to maintain the surface roughness, do you do corona etching or is there any other process?
So to maintain the surface roughness, generally we depend on machining process as much as possible.
Okay.
Then there is a baking, take it to very higher temperature to reduce any gas entrapment, which results a roughness later on. Then we take it to electropolishing to obtain the surface roughness.
Okay, thank you.
Yeah. So now this X-ray insert, so what we have discussed so long is that vacuum bulb. That has to be integrated into a metal part because we cannot simply, it's commercially not viable. So that part we call casings, which get integrated the because it's a rotating anode, so we have all this motor integrated in this part. And here this is basically oil filled device, and generally transformer oil, same high voltage and cooling purpose, same concept of transformer used here. And also, apart from the oil, solid insulations, like you can see, this is a solid insulations which is used here to strengthen the insulation breakdown between the high voltage part, breakdown strength between the high voltage part and the ground part. There is a criticality to ensure that oil does not create any air bubbles during its production life or service life, due to temperature coming and hot and cooling effect. There could be a possibility of bubble creation because of oil volume changes due to the temperature. So there is a critical design, what we call bellow, or the diaphragm, which take care of that oil extra expansion and contractions, and that results no air bubble or void creations during the operation life. Those voids not only bad for losing the high voltage step insulations, very dangerous in terms of image artificial effect. Any bubbles, if somehow created, doctors will see some abnormal thing on their screen, because that himself will reflect as a uh, disabnormalities or some problem in the patient body. Yeah, so we talk about that polymeric insulation, that's like a thermoplastic insulation is being used, and with typically 12 to 16 kilovolt and experimentally obtained value, not by theoretical value. For oil strength determinations, same guideline what normally people use in transformer industry, that Weidman curve guideline that is used, which give us good confidence that it will work even the oil quality goes a little bit bad during his lifetime. And it is the same guideline, even though it was originally developed for transformer for AC applications, but we find it is equally at least giving a good result or safe result in DC in X-ray tubes as well. So with that, we concluded the X-ray tube part. So we are here, which really produce the X-ray. Now, as we say that X-ray needs a high voltage, 40 kilovolt to 160 kilovolt. It needs a power to rotate because rotating anode. And it needs so many things like filament drive to thermally emit the electron, means light up the filament. So all this power, there is something called X-ray generator, which has input as 3-phase or some cases single phase domestic supply. And job of this block is to create all those required power supply. So that's like a power electronics, or I will say it's transformer people very close to that. So it's the same concept, stepping up the voltage from domestic level to till that 150, 160 kilovolt. Use a bridge rectifier to make it DC. But it is a super simple thing what I am showing. It's not, it's for understanding, but it has so many other criticality to take care. And what I wanted to point out here, so extra generator, if I look into a electrical point of view, it's a combination of power electronics and high voltage. So power electronics boards, generally it operate at maximum 300 volt, 400 volt, but here they need to produce at the end 160, 150 kilovolt. Hence they are all immersed in the oil, and some special care to be taken in the board, raw PCB design. So all the high voltage concept what we use in insulator design in power industry equally applicable here. So even in the board level, we need to ensure the creepage, clearances, even the tracking, tracing, all those things. And not only that, when it sum up, we need to take care of the stray capacitance effect, because you actually move into high voltage zone then. So that's how the typical boards will look. X-ray tube boards will looks with all this kind of separator or slot cutting to ensure that we obtain the proper creepage and clearances.
Also, sir, the creepage for, because we are dealing with high frequency here, somewhere around around
Kilohertz.
above 100 kilohertz.
Mm.
So that would naturally reduce the creepage. So would you rather suggest the lightning creepage? So for insulators, we have lightning creepage and we have AC power frequency creepage. So would it
Exactly.
be more closer to lightning creepage than power frequency creepage?
Yeah. On the DC side boards, we have to use those high frequency creepage guideline, and every industry have basically their own guideline. It's not anymore like a IEC standard and I follow that. So here mainly it is different company, GE, Siemens, Philips, they have their own guideline. So in AC side, those thing matters. And when it get rectified on DC side, because in DC side also the lot of measurement circuit will be there we follow a different guideline, which is applicable for the DC site.
Okay, thank
Yeah.
you.
So then all high voltage people, we know it's not only the design, the process play a major role to really obtain the high voltage. Just a quick time check. Yeah, I think still we have 15-20 minutes. On the DC high voltage design, not only design, the process are equally important. So there is like baking to demoisturize, oil filling, air bubble removal, and all these things needs to take care. Then only the power supply part of the X-ray device reach to a level where it functions satisfactorily. So yeah, these are some of the points what we discussed: solid insulations, liquid insulation, tightness of high voltage connections, oil layer thickness, filling process, and PCBA manufacturing. With that, I came to the end. However, I will just take few minutes, since we still have at least 15 minutes time, to show you some of the what we discussed so far are theory, all high voltage parts. When it comes in the product level, this is how it looks like. So this is a typical operation theater, you can say. This is a complete X-ray system. This system is a Philips system, and it has the monitor where you see the digital image processed from the X-ray output. And somewhere here, the X-ray tubes, what I discussed so far, which generate the X-ray, will be here. And this part, number 4, is detector. So old days, you know, that black film, and now it is digital detector. So it just come into here, and then it gives the required signal to see everything in the monitor. In this part of the operation theater, the generator is kept out, little bit away from there, from where the high voltage part come and power up the X-ray tubes, which is somewhere here. Another X-ray device is the CT scan, where you can see this is that board, what we call board. Patient lies here, and if I open this board, it looks the combinations of all our technical thing, X-ray tubes, generator, detectors, all these things. I will take little bit time to show you an interesting video. Let me know if this, if the my YouTube screen is visible now.
No.
Maybe I will share. Yeah, just give me a minute. Is this visible now?
Yes.
It is me.
So what I show you previously, that's the open part of a CT scan, and this is how you can see it. So maybe the audio was not audible, but it's okay. I will just explain. So this is what we were. Yeah, this is that inside of a CT scan device, which is, again, it's all high voltage and power electronics inside. And it just start rotating with very high speed, and it takes lot of snapshot of a 3D object. This is the human body, and it is taking the snapshot on many 32, like 64 slice means 64 images in one 360 rotation. 128 slice means 128 images in these 360-degree rotations. And then they stitch all the images together and produce a 3D model. So after all this X-ray, that all data feed into image processing software. It's a big part of the engineering team who has to take care of that part, and then it produces a 3D model of the object, and it rotates with a very high speed. The reason for this high speed is as we know that human body is not standstill. Your heart is between systolic and diastolic, it's expand and contract. Accordingly, all the veins also expand and contract. So if I have to take it, if I have to stitch one image which is at expanded condition, another image at contracted condition, it creates error during stitching. So ideally, you should have the images where an insignificant change in the shape happens. So it minimizes the error during this image processing. So that's the reason earlier it was 32 slice, now 64 slice, 128 slice. So more the number of slice, better the probability of any error, not having the error. Another extra device what we see, this is a what normally people call it C-arm, even doctors call it C-arm because it looks like C. And you have that X-ray producing device here, the detector here, and then yeah, it's the same way. Finally, digital thing. It's used for any kind of orthopedic surgery, or even for the any stent positioning inside the heart, or heart surgery without opening the heart, that kind of applications. Yeah, so with this, I came to the end of the presentation. So let me know any comments, anything I need to explain on that. Very happy to do so.
Hi, Balaji here again. So what is the typical exposure time?
Yeah, it depends. See, if it is a radiographic, so radiographic is similar to our standstill camera. So generally, there it's always come in order of milliseconds. So it can be as low as 10 millisecond, 20 millisecond, like that. It not only depends on the technical capacity of the device, it also depends on the human physics, thickness of the body, or the part you want to take. And now radiographic is the most earlier form of the thing. Now people have moved to CT and C-arm. C-arm is used 8 hours, 9 hours continuously. Patient is under exposure because doctors are doing the surgery in a, I will say, non-invasive way nowadays. Earlier it used to, and they have to rely on that feed, the camera feed, which is coming out of the X-ray devices. Then CT scan. So there are different type of scan, like it's only 360-degree scan, or it is like this, patient is coming and going back. And there could be a combinations of both, which we call helical scan. So there are different exposure for those applications.
Is it electronically controlled, or for example, the shutter is mechanically controlled?
No, it's all electronically controlled. No mechanical control.
Okay.
Yeah.
Hello, sir. It's Chirag. I have some practical questions. First, before applying high voltage to the X-ray tube, the filament needs to be reheated, right? So typically, what kind of lag time is there? Like before applying the high voltage, how much time before the filament is preheated?
Right. Very, very appropriate questions, I will say. So before applying the high voltage, filament temperature needs to reach to a level which is typically 1800 to 1900 degrees centigrade, which ready to emits the electron. So it's all this thing is controlled by the X-ray controller. Before even applying the high voltage, a command come from the device which we call preparations, and it pump a boost current first, which is very high current for few microseconds, and then fall down to a current which quickly take the temperature to that. So boost current is to take the temperature quickly to the 1800 degrees centigrade, and then high voltage exposure. Not only filament, rotating electrode. So the acceleration time of the motor also been programmed in such a way that unless the rotor speed reach to proper RPM and filament is not reached to that temperature, high voltage will not be on.
Okay, is there any way to fine tune this timing, that timing and both the temperature boost current maybe? Like if we observe the radiations or something like that.
No, that users, technicians, doctors, that's not their scope. It's
Now,
all
from
taken
point of view
from
only.
yeah, it's all done by the manufacturer of the device, and they have different program for different type of shot, because doctors use KVMA combinations, and for different KVMA shot there is a different program pre-programmed, and all happened in that level. As a manufacturer, yes, we do some engineering optimizations to optimize those things, and once it is yes done, released, verified, then that table updated.
Okay. One last question. Uh, Throughout the life of the X-ray machine, maybe a radiographing machine, do you frequently need to change the transformer oil or maybe oil insulation or X-ray tube, or is it good enough to serve the service life?
Well, so X-ray tube is a kind of replaceable component. Generally, high voltage instability is the major failure mode, and generally 3 to 5 years or 3 to 6 years maximum it will be changed in a system. So entire system remains same, tubes, new tube, no oil filling or anything in hospital or in site. It can only possible at back home, means at factory. And so any oil filling, oil top up, nothing done in application area. On high voltage tank, again, one of the major failure is high voltage instability, but due to the but high voltage tank is having a much higher life, 3 times, 4 times, means 20 years, 25 years. And in case high voltage tank, it is diagnosed by the service engineer that it's something happening on high voltage instability, no repair work at site, it's done in factory.
Okay, thank you very much.
Yeah. Yeah, so with this, I will stop sharing.
So thank you.
Yes, so if there is no further question, yeah.
Sorry for the interruption. So thank you again for explaining the high voltage design aspect related to extra device, and the session was quite detailed and elaborated. I would encourage other participants to ask the questions meantime and fill the feedback form in the chat box. So I would like you to advise us, the young professionals who are at the early stage of starting our careers, to how to navigate our careers between industry and academia, because most of us are PhD scholars or research scholars. So And also you have also completed your PhD. So how would you suggest us to navigate our careers, and if you have some tips to share?
Yeah, I am also just like one of you. In fact, I have visited IIT Kanpur when I have just completed my PhD and I came back to India. And what I remember mostly, it was something similar to this kind of forum. It was long ago. And yeah, so what I feel, it's when we come out of the university or the college, we really enter into professional life. There are some initial mismatch happen as per our expectation and as what we are getting. It's important to stay tuned, take that hit at that time, few years, and then especially these MTech, PhD professionals, it's important to learn at that time whichever area you are and try to correlate your learning with respect to product. When you get into the industry, the product design, product manufacturing, product engineering is a different, some new thing you will see. However, the basic remains same. So it is possible for a person to really correlate after few years, whatever learning they have, they are really able to apply them. And if you see, if it is not really getting correlated, so there could be two reasons. Either you are not in your field which you have studied, or your natural orientation is towards management, not towards the technical thing. Two of these things happen. So when I come out, I entered into X-ray device, and I still remember I told to my interviewer, well, I have read X-ray only during my school days. Nobody has a X-ray subject in my BE or master degree or PhD time. However, in the course of time, I could able to correlate easily many of the things which I learned during my time of study. And of course, there will be some more new dose, new medicines, new way of thinking, new way of problem solving, what people learn at the when they get into the industry. And it's not, when you complete your educations, it's not the end of learning, it's just begin at that time. And it's always that learning still goes on till the time you are working. So I wish all the best for all the professionals who will soon become my colleagues in industry. Maybe some of them maybe from go to academic, but I wish you all the best.
Thank you, sir. There is another question in the chat box from Chirag. Any comments on carbon nanotubes? Would they replace the conventional tubes in the near future?
Well, that's a very good comment. Actually, when even a few weeks back, I was talking with one of the young person who has joined in our team, and when we together was looking, we find there is the conventional filament they are trying to replace with carbon CNT, and there are certain advantage. It has been reported, but at least I am not aware at this point of time anything commercially available. But yes, it's some research work, and the study says yes, it's a kind of second generations or the next generations of filament. So what I saw today, that roll type of conventional filament, already many commercial applications we use little bit advanced design, and more advanced design will be that carbon nanotube. Yep.
So, adding to this question, how do emerging technologies would influence the design and functionality of HV ray systems? HV X-ray systems.
See, the emerging area, that one of the topic is in X-ray tube related is material science. So that anode metal is a topic where things need to be really improved in terms of better life of that. In terms of high voltage stability, I think it's all compact design we can go, provided we have very good solid insulation developed with some filler or something on that. And in another thing what we can one is another very important thing is X-ray device cannot use any kind of thermoplast. Any normal thermoplast degrade, normal insulation degrades, so it needs some special plastic to not to get degraded in the presence of X-ray. And there is, in my knowledge, only two or one, I know only one type of thermoplast who has that property. So anything on that aspect, maybe someone will do, which gives extra stability and high voltage stability both.
But sir, isn't alumina used for the insulating purpose? So you are saying that the thermoplastic is used. So what about aluminum?
Yeah, there are some composite insulators is used, but always there is a risk of degradations. That's why we are very careful to check the life when we use the composite insulator. And in the direct X-ray paths, there is only one type, what we call Ultem. It is a, I think, Lexon material, which direct X-ray it can withstand. Not I am not heard about any more thing. Which are not in direct X-ray path, we do use the composite insulator, what you're talking, the doped one, and that also need to be really life tested before commercially use that.
Also, during the process of electron bombardment, not just X-ray will be produced, right? There are a lot of frequency, a lot of wavelengths will be produced. So, how do you commercially manage to arrest those frequencies? You use a phosphor coating, or like what exactly? What do you use?
Yeah, as you say that there will be some X-rays, some rays which are a little bit softer side, and that's the reason in any X-ray device there is a something called inherent filtrations which we specify. So we do not use any special coating to arrest those radiations, those extra low or soft X-rays. We use a filter to arrest them inside the X-ray tube, not to go out for the patient level. And this arresting is done in various levels. One is inside the tube itself, we use some filter to arrest them. Then there is something called collimator, which also act to absorb soft X-rays, and then it hits the patient, then it goes to diagnostic parts. Even in the diagnostic plates itself, some of the unuseful rays which may create a image artificial effect, there is a provision to arrest them. But this all done by physically blocking them, not by any kind of coating or anything which will not allow to emit those rays.
Yeah. There is another question by Chirag in the chat box. Is Philips working on any substitutes of lead for absorbing radiations?
Yeah.
Considering lead is, it is.
Yeah, that's a very good question. Looks like Chirag might be having some experience on X-ray related industries. That's why he's asking a lot of pertinent questions. So there are some polymer based material which long back 15 years ago I heard people are working to develop that. And e-commerce is one of the thing what you can search in internet. You will see that e-commerce is a brand name of some composite polymer which is claimed to be like lead. So long, one is we use the lead to protect the emissions of the X-ray, because X-ray tube will have that lead lining and all these things. Second, as a second level of protections, doctors also wear apron. Earlier it was lead apron, so they used to have it, and now I heard that they are switching to polymer based apron which are less bulky, less weight, and good to protect them from scattered X-ray. So one is direct emission of X-ray, and second is scattered emissions of X-ray, which doctors need to be protected, and they wear those aprons. I heard recently that there are those kind of things applicable for this, but at least in Philips, nowhere it is used as blocking the primary rays.
So, adding to this question, is it because the new materials performance and reliability is not good as compared to the
The
traditional?
blocking, the X-ray blocking capacity has not yet gone up to the lead, what it can do. That's why the lead is the restricted metal, but still due to limitations of technology, it is allowed to use in X-ray applications. So still that blocking capacity has not yet proven up to that level where it can be commercially launched.
Okay, thank you.
Hello. Yes, this is Ashok. I just have a question related to image processing. Out of curiosity, sometimes doctor suggests us to drink a lot of water before CT. So does that has to do anything with the image, maybe image overlapping or something?
Well, that's a question typically for doctors. So I am not also very sure, but what I can feel, X-ray works on the density difference of the image of the object which needs to be imaged. And if you really interested to really understand the veins and arteries, etc., they need to be really expanded. I feel, don't trust my answer. That's one of the guess I give you. I am not our real. I do not have the authentic answer for this.
Okay, thank you very much.
As I would like to wrap up this webinar, if there are any further questions from our speaker, if it is possible, Dr. Das, can you share any of the communication detail, like your link?
Yeah, I think my email ID already Darshan will be having, so it's okay to share.
Okay, so Darshan, you can post the email ID in the chat box. If there are any further questions from our speaker, they can directly communicate with them. So it was our pleasure to have you on board, sir. So in this regard, I would ask my team of IEEE student branch to present a virtual token of appreciation. Team, please.
Okay, just give me a moment. Maybe I will take a snapshot of this.
We will send it to you via mail also. You can take the snapshot.
Yeah.
With this, I would ask all the participants to please switch on your camera for a moment to take a group photo in form of a screenshot. Should we wait for others or should I take the screenshot? Okay, I'll take some, and if somebody else switches on.
Yeah, it's done, Professor.
It's done? Okay.
Yeah.
So thank you again, sir, for the wonderful webinar. It was quite interactive. And I also acknowledge the efforts of our entire team and IIT Kanpur for planning this webinar, and the sincere gratitude to IEEE IIT Kanpur student branch and UP section for their support, and our faculty advisor, Dr. Alok Ranjan Verma, and our mentor, Dr. Nandini Gupta, for providing valuable guidance. No event is complete without our lovely audience. I thank all of you for being with us. Have a nice day. So thank you very much. With this, I'm closing the webinar. Thank you, sir.
Thank you. Thank you once again for giving this opportunity. Okay. And hope we will again have something later. Okay.
Yes, sir.
Thank you. Good evening to all of you. Bye-bye.